Okay, in this video, I want to talk about definite integration when you're integrating over a different region other than rectangles. So remember, when you're integrating with functions of two variables, it's the region could be a two-dimensional shape, right? It doesn't have to be a rectangle. It could be a circle, it could be a triangle, and other geometrical shapes. Setting up the boundaries for these integration is tricky. And especially when you want to switch the order of integration, it's very counterintuitive. So let's get right to it and see if we can practice a few. Fair warning, this is a subtle, tricky subject. So use the advantage of recorded lecture. If you feel like you didn't get all of it, you can rewatch the video, use pause, rewind, and see if you can work through the same problems that I'm doing in front of you on your own. Okay, let's jump to the problems. Okay, so I'm gonna run through a few problems and set up the problem with you, and hopefully you could do some on your own as well. Okay, so let's say we're looking at this double integral, x plus y, on a domain that looks like this. Okay, so when you have y that's between 0 and square root of x, you can think of this y as being trapped between the bottom curve 0 and the top curve square root of x. And y equals square root of x is the top. So let's try to draw this. So this is the domain. Y equals 0 is the x-axis itself. And y equals square root of x looks like that. Okay, so we're looking at the y values between these two curves that's trapped between the two. And we also know that x is between 0 and 4. So origin 0 and here's 4. So we're looking at that shaded region. Okay, and when x is equal to 4, the y value is equal to 2. So that's the region we're looking at. Okay, so here's how to set up the integral. Okay, I'm gonna set this problem up twice. Once integrating with respect to y first, and then integrating with respect to x second, and then the other way around. Okay, so we need to set up these 4 limits of integration, and there's rules for what we can do here. Okay, let's set up dy dx. Okay, here's the inner integral, and that's the outer integral with x. The outer limits could only depend on constants, like 0 and 4 here. So that's when we're talking about x, we're talking about the leftmost value. And the rightmost value. Okay, and that's what comes on the bottom and upper limit on the outside. So this is going to be from 0 to 4. So that doesn't seem too strange so far. With the inner limits, when we're integrating with respect to y, we're talking about the bottom and the top, right? So the bottom curve is y equals to 0. And the top curve is y equals square root of x. Okay, and You might think this looks strange right here. You are allowed to use the variable on the outer integration. So as integration limits, right? So you are allowed to write square root of x here, but you are not allowed to depend on the outer limits, cannot depend on the inner variable, if that makes sense. You could only, the inner integral could depend on the outer, and that's the only direction you could do that. All right. Okay, let's set up the other direction. Okay, so you could set up the exact same integral. Okay, so here it's tempting to say, well, I've already set up one way. Don't I just switch the limits from the inside and the outside? Well, if you do that, then you have square root of x. So the outer limit is depending on the inner variable, which you're not supposed to do, right? Okay, so what do we do? So instead of, when we're looking integration with respect to x, instead of integrating from bottom to top, x is going to integrate from left to right. So you look at the region, and this curve right here, it's the top curve, but it's also the left curve, right? And this is the right curve of the region. Okay, so we're integrating from left to right. So we're going from y equals square root of x to x equals to 4, that's the right curve right there. But instead of writing y equals square root of x, we want to solve for x in terms of y, because x can depend on the outer variable. So it's going from y squared up until when x equals to 4. And then for the limits of integration for the outer variable, so y, this is the bottommost value and the topmost value. So the bottommost value in this region is y equals to 0. And the largest y value that's given is 2. Okay, and the outer limits are always constants. So I think that's the easier half when you're doing this. Okay, so I hope that made sense. Let's integrate this. I don't know which is easier. I'll just do the second one. Okay, but I should get the same answer either way. So antiderivative of x plus y with respect to x is going to be x squared over 2 plus xy, where x goes from y squared to 4. Okay. So if I plug in 4, I get 4 squared is 16 over 2, so 8 plus 4y minus, if you plug in y squared into x, y squared squared is y to the 4th plus, if I plug in y squared into the x here, I get y cubed. Okay. Now I integrate each of the terms with respect to y. and y is changing from 0 to 2. Okay. The rest is arithmetic, so I don't want to follow the calculator to finish this problem. But I trust that you are able to finish this problem. But the setup is the difficult part. So try it with me on the second problem. Okay, so this time the domain is given here. Okay, so remember, if y is trapped, this is the bottom curve, and this is the top curve. So everything is between y equals 0 and y equals 1. And when x is in the middle, we're talking about it's going from left to right. Okay. All right. So we can set up both integration. Okay. So this is the integral I want to do. Let's do dx dy. And we'll also do dy dx. Okay. And I want to draw this as well. Okay. Let's see. So the left curve x is equal to square root of y. That's another way to say y is equal to x squared. So this is a parabola. Okay. That's the left curve. And the right curve is x equals to 1. Okay. So we're trapped between those two curves. Okay. And then the bottom is 0, and then top is 1. And I believe that's where it intersects. So this looks good. Okay, let's see. So if I'm integrating with respect to x first, x is going from square root of y to 1. So that's the inner limits. And the outer limits, y is changing from 0 to 1. So that's one way to set it up. The second way to set it up, now if I want to integrate with respect to y first, I want to go from the bottom to top curve. So the bottom curve is y equals 0. And the top curve, which happens to be the same as the left curve, is x squared. Y equals x squared. So it's going from 0 to x squared. And x is changing from the leftmost value is 0 and the rightmost value is 1. Okay. All right. So these are the two ways to set up the problem. You might be wondering, well, don't you only have to set up once? And that is kind of true, but they're not created equal. One of these integral is impossible to do, and the other one, it's doable. So if you have happened to set up the first way, which might be the most natural way to set up because of the way that the domain was given, you might think, oh yeah, let's integrate with respect to x first. But you look at the integrand, and y is a constant, so you could just pull that out. But integrating 1 over x to the 5th plus 1, there's no technique that we learned in Calc 2 that allows you to solve this problem. There's no U substitution or table that you could use. But if you look at the second one, now if you're integrating with respect to y first, then now x is constant. So you can pull, so you can pull out 1 over x to the 5th plus 1. You can pull that out. And at least the first step is much easier. So the antiderivative is y squared over 2. And y is changing from 0 to the x squared. And when you plug in x squared into the y squared, you get x to the 4th. 1/2 is a constant, so I can pull it outside. Okay. And now that we've come to this part, now u substitution works, and then we can finish this problem. If you say u is equal to x to the 5th plus 1, du is 5x to the 4th plus 1 dx. Oops. The derivative of 1 is 0. So you have x to the 4th dx that appears in the numerator. And then 5, we could just make up for it by dividing by 1/5. So we have 1/10 on the outside. 1 over u du. And if u is changing, if x is changing from 0 to 1, then u is changing from, when x is 0, this is equal to 1. And when x is 1, this is u is equal to 2. So antiderivative is natural log of u, and u is changing from 1 to 2. Okay, and natural log of 1 is 0, so we just have natural log of 2 divided by 10. Okay, so this problem was only doable setting it up the second way. The first way didn't allow you to use substitution or any other technique. So sometimes you have to set it up both ways and see which one works. Or if you're able to see from the integrand which way you want to integrate first, maybe you could look at this and think, well, I can't integrate with respect to x first, so maybe I'll try y first. So that might inform you how you should set up the problem. Okay, all right. So how do you feel about the subject so far? I'm going to make it look a little bit more difficult now. Okay, so maybe it's not given to you as double integral with a particular domain. Maybe it's already set up for you as an iterated integral, but it's in the wrong order. As in, if you look at this, it's not clear how to integrate this. Well, actually, you might try u substitution. Oh yeah, you should set u equal to 1 plus cosine squared, but if you try to do du, by chain rule, you have to multiply by negative sign. And you think, well, there's cosine dx, but there's no sine, so I can't complete the u substitution. Okay. So you get stuck, right? So instead, what you could do is you can unwind, looking at the limits of integration. What region did it come from? Well, let's try to see if we can draw it. So let's see. We're integrating with respect to x first. So whatever comes at the bottom, x is equal to arc sine of y. This is the bottom curve. Sorry, x goes from left to right. So this is the left curve. And x equals to pi over 2. This is the right curve. So let's see if we can draw that. So x is equal to arc sine of y. That's the same thing as y is equal to sine of x. Okay, but only up until x is equal to pi over 2. So that's when sine hits 1. Okay. So that's the region we're looking at. And then y value is going from y equals 0 to 1. So 0 to 1. So that works out. Okay. So this is the region we're looking at. Let's try to set up the other direction. So we keep the integrand as is. We're going to integrate with respect to y first, then the x. So if we're integrating with respect to y first, we're going to go from the bottom curve to top curve. Okay, so the bottom, the x-axis is y equals 0, and the top curve is equal to sine of x. So 0 to sine of x. And the leftmost x value is 0, and the rightmost x value is pi over 2. Okay. All right, so how do we integrate this guy? Well, notice that the integrand doesn't depend on y at all. So this is just constant, right? So the antiderivative is the constant times y, and y is changing from 0 to sine x. Okay. So now this is the integrand. So it looks more complicated, but you might have noticed when we tried to do the u substitution, there was sign missing. Now we have that sign. So we could actually complete the u substitution. So if we set u equal to 1 plus cosine squared, du is 2 cosine x sine x. Actually, minus that. So if we do that substitution, we'll get minus sine x cosine x dx turns into just du. So square root of u du. And let's see, when x is equal to 0, if I plug in there, 1 plus cosine of 0 is 1. So 1 plus 1 squared is just 2. And when x is equal to pi over 2, if I plug in pi over 2 here, cosine of pi over 2 is 0. So 1 plus 0 squared is just 1. Okay. And then there's a negative sign in front, so we can switch the limits of integration. And antiderivative of u to the 1/2 is using the power rule. We get 2/3 u to the 3/2, where u is changing from 1 to 2. So 2/3, 2 to the 3/2 power minus 1. Okay. So that's how you can do that problem. Let's do another practice problem. Okay. Let's see. Okay. So cosine of x squared, again, there's no technique that we learned in Calc 2 that does this. So let's try to change the order of integration. Let's see. X is changing from left curve. So x equals to y is the left. And x equals to square root of pi is the right curve. So x equals to y is y equals to x. So that's that 45-degree diagonal line here. And x is equal to square root of pi. Okay. And y is changing from 0 to square root of pi. So 0 to square root of pi. So this is the region we're looking at. Okay. Okay, now y is going from the bottom curve to top curve. So bottom curve is 0, and the top curve is y equals to x. Okay, and then x is changing from 0 to square root of pi. Okay. So we can do this. So again, the integrand doesn't depend on y. So antiderivative is cosine of x squared times y, and y is changing from 0 to x. Okay, so x cosine of x squared. And if we subtracted 0, then we'll get 0 there. Okay, and then again, use substitution is the thing that works here. We'll get 1/2 cosine of u du. And if x is equal to 0, then u is equal to 0. If x is equal to square root of pi, then u is equal to pi. The antiderivative of cosine is sine from 0 to pi. Let's see. So sine of pi is 0, and sine of 0 is 0. So I guess we just get 0. Okay. So that's that problem. I could do any number of practice problems, but you as a student has to try on their own. So let me give you one challenge problem. Okay, so here's another integration to try. So again, this is set up in the wrong order. By what I mean by that is it's impossible to do this with integrate x first. So switch the order of integration. Trying to draw the graph, I think it'll help. And then if you do it correctly, the answer you end up with should be e to the 16 minus 1 over 4. So try it out. If you get stuck, ask the Discord, and we'll work it out together. Okay, so this is where I want to end the video. I'll see you later.